Hi students, welcome to today switching theory and logic design class, STLD class. In the last class we have seen the conversion systems introduction. In the last class we have completed decimal to binary conversion. In the last class we have completed decimal to binary conversion and binary to decimal conversion. The decimal number system base is 10. We can call base or radix. So anything we can call. So decimal number generally we are representing with like this. For example, 75 of base 10. So this is the decimal number representation. And coming to the binary number representation. So this is the example of binary number representation. So this is the base. This is the base. This is the base. Where here this base 10 is representing decimal number system, and where this number is representing the binary number system. So in the binary number system we know that in this number system we have only 2 digits. So for that reason we are representing the 2 as base, and in this binary number system we have 0 and 1 numbers only. So this is the binary number system and decimal number system. In the last class we have completed decimal to binary conversion and binary to decimal conversion. In this class we will see decimal to octal conversion, decimal to hexadecimal conversion, octal to decimal conversion, hexadecimal to decimal conversion, binary to octal conversion, binary to hexadecimal conversion, octal to hexadecimal conversions. So in the present day class we will see some of the possible conversions. Majorly I will discuss in this class these 4 conversions. In the next class we will discuss these 3 conversions. Alright, so first decimal to binary conversion. In the last class we have already seen this topic. Again I have taken a small number 47 of base 10. I want to convert into decimal. Here my motto is I want to convert a number into the binary. For the same number I want to convert into octal. For the same number I want to convert into hexadecimal. So for a number we will see how we can convert that information, right? So here see, for example, 47. We know that how we will convert decimal to binary is very simple one. We have to divide the given number with 2. So this is very simple. So see here, this is a 47 given number and we are dividing with 2. So when you are dividing this one, so 23 2s are 46 and 1 is the remainder. 2 11s are 22 and remainder is 1, and 2 5s are 10, so 1 is the remainder, and 2 2s are 4 and 1 is the remainder. 2 1s are 2, so there is no remainder. So there is no here 1, there is no chance of dividing this one. So for that reason I am represented 0. So now I got the remainders here. So these are my remainders. So these remainders we have to write from down to top. We have to write these remainders from down to top. That is 1 0 1 1 1 1 of base 2. So this is our solution. So here I have 47, this is base 10, and this equivalent binary number is 1 0 1 1 1 1. So this is the binary equivalent number. So this is the conversion procedure for decimal to binary. For the same number, for the same 47, we will convert this number into octal, into hexadecimal. How we can convert? How to convert these conversions? Now we will see. Right. Now, decimal to octal conversion. Decimal to octal conversion. The octal number system generally we are representing with base 8. So octal number system. Octal number system is consists of 0, 1, 2, 3, 4, 5, 6, 7. 0 0, 1, 2, 3, 4, 5, 6, 7. That is, in our octal number system, we have 0 to 7, total 8 numbers. So for that reason, we are using base as 8. In our octal number system, our base is 8. Okay, so here the given number is in decimal, 47 of base 10. Now we have to convert into octal number system. Now here, if you have your decimal number, if you want to, you have your decimal number and you want to convert into any number system, you have to, if you want to convert into any number system, you have to take that base for division purpose. Here 47 is the decimal number. You want to convert into octal, that is 8 base. So now you have to divide your number with 8. Now you have to divide your given number with the 8. So 47. Here we are dividing the decimal number with 8. So 8 5s are 40. 8 5s are 40. So the remainder is 7. So 47 minus 40. So the 7 is remainder. So there is no chance to divide this 5 number. So I represent it with 0 times and the remainder is 5. Now the answer is 57 of base 8. So this is equal to 47 of base 10. That is 47 of base 10 is equal to 57 of 8. So these two are equal numbers only, but we are representing with a different number system. So this is the answer. 47 of base 10 is equal to 101111. So this is the solution we got in the previous slide, and this is the solution we got in the present slide. That is, the decimal 47 is equal to the binary 101111, and that is equal to in octal 57, right? So if you want to convert into binary system, you have to divide with 2, divided by 2, and if you want to convert into octal system, you have to divide it with 8. Now if you want to convert into hexadecimal system, you have to divide with hexadecimal base. What is a hexadecimal base number? Hexadecimal base is 16. Right. So decimal to hexadecimal conversion, convert the given number 47 of base 10 into base 16. We don't know the number in base 16. So now divide this one like this. So 16, almost 16 to the 32, 16 to the 32, 47 minus 32, that is 15. So this is a remainder, but 15 we don't have in the hexadecimal number system. That is, this is the decimal multiplication and decimal divisions we are doing. So for that reason, the remainder is 15, but you have to represent with using hexadecimal representation. So see here, the 15 equivalent number in hexadecimal is F. So for that reason, this 15 you have to represent with F. And here the remainder. So here we have again 16. So there is no chance to divide this 2. So for the remainder, so 0 times the remainder is 2. Okay. So this is the final number. So the final answer is 2F of base 16. So the answer is 2F of base 16. For 47 of base 10 is equal to 2F of base 16. This is the solution. This is our solution. Now, so see here, I have converted from decimal to binary first. Next, I have converted decimal into octal. Next, I have converted the given number into hexadecimal. So, the decimal equivalent, binary equivalent, octal equivalent, and hexadecimal equivalent numbers are these numbers. Okay. So, this is the conversion procedure from decimal to hexadecimal. So from decimal to, if you want to convert into any number system, so from decimal to any number system, so decimal to any number system conversion. So for our decimal number system is 10, but if you want to convert into Octal, you have to divide the given decimal number with 8. That is, you have to divide with using for the given number. So this is some given number. I have represented with x, x, x. Okay. So if you want to convert into octal, you have to divide this number with 8. Otherwise, you want to convert into base 12. I said that we have 4 basic number system, that is binary, decimal, octal, hexadecimal. So these are the very basic number system. Other than this, we have a lot of number system. Any type of number system you want to generate, you can generate. For example, 12 number system is there. I am not giving any name. For example, consider that is a saturation. So the 12 number system I am representing as saturation number system. So I have saturation number system. Now the given number I have in this saturation number system I have totally 12 different types of digits. Now if you want to convert the given number from decimal to in the saturation number system, that is 12 base number system, you have to divide with 12 for the given decimal number. So this is a standard procedure. You want to convert from decimal to any number system, you have to divide that number system base. This is the major principle behind this. Next, octal to decimal conversion. Octal number system to decimal number system conversion. For example, I have taken For example, I have taken 3201 here. My problem is 3207 of base 8 is equal to what is the number in decimal. So this is my problem. 3201 of base 8 is equal to what is the number in decimal. So for that you have to use the standard procedure which you have used for the binary to decimal conversion purpose. So you can take the standard procedure. Now 3201. So these are the 4 digits are available with the octal number system. Now you have to convert the given number into the right. So in the binary number system, I said that this is LSB and this is MSB for the given number. If it is in binary, you have only zeros and ones. If it is a octal number system, here the values may be from 0 to 7, any number, okay, except 8 and 9. The remaining all numbers are available in this place. Okay, so for the octal number system, in the octal number system, this is the least significant bit, this is the most significant bit. Okay, what we did there, we have divided if our first number 1 into 2 power 0 that we converted previously for the binary binary to decimal conversion. The same procedure we are using. In the place of 2, we are using 8. Okay, binary to decimal conversion, that is base 2 to decimal conversion. So when you are converting into decimal, when you are converting from any number system, that base you have to take and you have to multiply with that base number system, power 0, power 1, power 2, like that. If it is binary, 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, 2 power 5, 2 power 6 and so on, 2 power n. This is the octal number system. So octal number system base is, we know that 8. Octal number system base or radix is 8. Now you have to multiply each the LSB digit with 8 power 0. The next LSB bit you have to multiply with 8 power 1. Next LSB bit you have to divide with 8 power 2. Next you have to go so on like this. Okay, right. So the first digit, the 1 I have placed here and I am multiplying with 8 power 0. Next digit 0 into 8 power 1. Next digit 2 I am multiplying with 8 power 2. Next value is 3. Next digit is 3. 3 into 8 power 3. Okay, right. Now multiply these values. 8 power 0 is 1. 8 power 0 value is 1. 8 power 1 is 8. 8 power 2 is 64. 8 power 3 is equal to 5. Okay. So 1 into 1, 1. 0 into 8, 0. 2 into 64, 128. 512 into 3, 1536. Sum all the values. Sum all these values and you will get the total sum value. Right? Total sum is equal to 1665. Right? Now the solution is 3201. So this is the given number. So this is the given number and this is the final answer. This is the final answer. 3201 of base 8 is equal to 1665 of base 10. How you got this 1665? You have taken the sum of all the each bit you are multiplying with that particular base number system, that is the radix with the power 0, power 1, power 2, power 3, power 4 from LSB side. From LSB side, each bit you are multiplying with that particular number system with the power 0. That is, you have to start from the LSB. From the LSB first bit digit you have to multiply with 8 power 0. The second digit you have to multiply with 8 power 1. Next digit 8 power 2. Next digit 8 power 3. Like that you have to multiply. What we did in the binary to decimal conversion, the same procedure you have to apply. So the subject is very, very easy. The procedure is common for any type of number system. The procedure is common for any type of number system. Still we have some more easy conversions. Some more easy conversions to learn to convert these numbers easily. That also we will see now. Right. Next, hexadecimal to decimal conversion. Hexadecimal means what is the number system here? The base is here 16. Here the base is 10. That is, for example, if you have some number, okay, some number is there, that is base with base 16 and with base 10. You have to convert. How to convert this number? So here you have to see. You are converting into decimal. Okay. So from which number system? Hexadecimal number system. That is, so for that reason what you have to do here. So when you are converting from decimal to any number system, you are dividing with that particular number system. That is any number system. Okay, from any number system you want to convert into decimal, you have to multiply with any number system. Okay, so the decimal, you don't touch the decimal. So you want to convert from decimal to any number system, you have to divide with any number system. If you want to convert from any number system to decimal, you have to multiply with that any number system. That is the very simple logic is behind in this number system. Okay, right. Now we will see one example in this method. Okay, for example A3. So here the problem is A3 of base 16 is equal to what is the value in decimal? What is the value in decimal? What is the value in decimal? Right? So this is the conversion we have to do here. So A3. The same procedure what we did for octal to decimal conversion, for binary to decimal conversion, the same procedure we will apply here. A3 is equal to, here the first digit we are multiplying with 16 power 0, the next digit A is we are multiplying with 16 power 1. So 3 into 16 power 0, the value of 16 power 0 is equal to 1. There is no problem. A. What is the A value in decimal we are representing? In hexadecimal, that is A. In the decimal, the A equivalent value is 10. Why? Because 0 to 9. After 9, in the hexadecimal, we have A, B, C, D, E, F. A is equal to 10. B is equal to 11. C is equal to 12. D is equal to 13. E is equal to 14. F is equal to 15. Okay, so in the previous examples we did some F calculation. The remainder we got 15 and the 15 we are representing with F. Okay, here A value is 10. So A value is 10. 10 into 16, that is equal to 116. So 3 into 1, 3. 10 into 16, 160. So the final value, total sum is equal to 163. Total sum is equal to 163. So this is the hexadecimal to by hexadecimal to decimal conversion. So here it is wrong. So this is the hexadecimal to decimal conversion. So this is our hexadecimal number, and this is our decimal number. Okay, 83 equivalent value in decimal is 163. So it is very simple procedure. It is very simple procedure. So hexadecimal to decimal conversion. Right. Total we have 9 conversion techniques. In that we have completed 2 conversions in the previous class, and 3, 4, 5, 6, 4 types of conversions now we did here. Next, 7th conversion. Binary to octal conversion. Next one is binary to octal conversion. Right. Binary base is 2, octal base is 8. That is from base 2 to base 8 conversion. We don't know, some value is here, right? I have given some value in binary. Now you have to find the value in octal. Okay, this is our target here. So here we have written 8 is equal to 2 power 3. So our base number system in our binary number system we have 2, and the octal number system is 8. So the octal number system is 8, and we can represent that is with using 2 power 3. And see that octal numbers equivalent binary numbers. So 0 equivalent binary value 0, 0, 0. 1 for 1 equivalent value 0, 0, 1. For 2 equivalent value is 0, 1, 0. For 3 equivalent value is 0, 1, 1. And 4 equivalent value is 1, 0, 0. 5 equivalent value is 1, 0, 1. 6 equivalent value is 1, 1, 0. And 7 equivalent value is 1, 1, 1. In the last class we have seen why these numbers we have written. Otherwise you can use your decimal to binary conversion. For example, take 4 value. In decimal and octal, for 0 to 7 there is no changes. Okay, right. For example, 4 of base 10 is equal to what is the value in binary. So divide this value. 2 2s are 4, so remainder is 0. Next, 2 1s are 2, so the remainder is 0. Wait. Right. 2 2s are 4, the remainder is 0, and 2 2s are 1, and the remainder is 0. Next, you can't divide this 1 by using 2, so for that reason 0 times the answer is 1. Now what are the values you have obtained? That values you have to write from down to top. So 1 0 0. So this is the binary equivalent number for 4. So what is the value for 4 is here? 1 0 0. 1 0 0. Right? Okay. We can use one more technique from decimal to binary conversion also. Okay. For example, you want to know the value equivalent for 13 in decimal. What is the value in binary? For example, 13 of base 10. You want to know this value. Okay, it's very simple thing. You have to follow 8421 code system. You have to follow 8421 code system. For example, you have for 1101. For example, you have 13 equivalent value you want to know in binary number system. So by adding these numbers, you have to get 13. So which digits you have to add for getting 13? 8 plus 2 10. 10 plus 1, you will get 11 only. So it's not possible. 8 plus 4, 12. 12 plus 1, 13. Okay. If it is 1, if it is 1, if it is 0, if it is 1, you will get the value 13. You will get the value 13. That is 1101. So 8 plus 4 plus 1. 8 plus 4 plus 8 plus 4 plus 0 plus 1. That is equal to 13. Okay, so this is very simple formula for recognizing any number, okay, from binary to decimal, right? But here concentration is, I have a binary number. I want to convert that binary number into octal conversion. Okay. For example, I have 10110.01 of base 2. Okay, I have taken here integer and fractional parts. Both parts I have taken. Okay, so see here, the octal numbers are 0 to 7. Okay, the binary numbers are here from 000 to 111. Okay, 3 digits we have taken here, right? As per the power, see here, 2 power 3, I have taken 3 digits. By using 3 digits, I can represent the maximum possible combinations of this 8. Can I represent other than these combinations by using zeros and ones? We can't represent. See, for example, I have 3 bits, B3, B1, B0. Okay, so the maximum possible combinations, how you will get? Here you have 3 digits. So 2 power 3, you will get 8 possible combinations. So here this is the maximum possible combinations. For example, you have binary data, for example 16 bits, you will get the maximum possible combinations are 16. If you have 32 bits, you will get maximum 2 power 32 possible combinations. So this is the maximum possible combinations. Right, here our we have to convert our binary number into octal number system. So it is very simple calculation. Okay, so just take group the given number into three digits. Okay, so from decimal, see here, this is very important point. Decimal point. Very simple. This is the decimal point. From this decimal point to for the integer part. So this is the LSB bit. This is the LSB bit. Okay, from this LSB bit, for 3 bits you have to make a group, and next 3 bits you have to make a group. Sir, here I have only 2 bits. I don't have any 3. I don't have 3 bits. What I have to do? So this is your question. So put simply a 0 here. Just put simply a 0 here. Okay. Why? Because if you add left side 0 for integer part, it's not a big problem. So 0 1 0 1 1 0. The value of this one is 6. See here, 1 1 0 6. Next 0 1 0 0 1 0 value is 2 2 6. Next, from this decimal point, from here, from this bit to, you have to make 3 bits. Don't come from the right side. You have to go from decimal point to next. So here I don't have any digit. Put 0, no problem. For example, 0.25, right? For example, here we have some 0.25. 0.25. So this is equal to 0.250, right? .25 is equal to 0.250. Okay, this is equivalent value. 0.25 is not equal to 0.025. Okay, so this is wrong. You can add right side, you can 0 for the fractional part. Right. So now make three groups. I have made here 3 groups. I have made 3 groups. I have made 3 groups. Next, for this three group equivalent, so I have placed 0. I am assuming zeros here, and this is 6, this is 2, and this equivalent value is 2. So the total final value is 26.2. That is the given number is 0.010 of base 2. So this is the given binary number, and finally you got 26.2 of base 8. So this is the given number, and this is the obtained value. Okay, so here you can convert from binary to octal in this way. Otherwise, you can convert from the octal to binary in this way. Okay, for example, 26.2 is there. For 6 equivalent value 110, for 2 equivalent value 0, 10 and dot 2. So 2 value 0, 10. Okay, so you got the same value, right? You have an option to convert from both directions. It's not a big problem. Works on both ways, binary to octal and octal to binary. The same principle is used for in the both directions. Okay, thank you. Next we will see binary. Hi students, our next topic, binary to hexadecimal conversion. Binary number system, that is we are representing with base of 2. For hexadecimal number system we are representing with a base of 16. So that is for a given number with base 2 you have to convert into base of 16. For example, this is the hexadecimal number representation. This is the binary number representation. Now, of base 2 is equal to what is the number in hexadecimal? Right? I have some binary number. Okay, I have some binary number. I want to convert that number into hexadecimal number system. So this is our main motto. So that is base of 2 to base of 16 conversion. Simply you can call the binary to hexadecimal conversion, of otherwise you can call base 2 to base 16 conversion technique. So now here the 16, by using 4 digits I can represent the maximum possible combinations. I said that in the previous slide, for example, I have 3 bits, the maximum possible combinations is 3. If I have 4 bits, I can represent the maximum possible combinations are 2 power 4. If I have 5 bits, I can represent the maximum possible combinations are 2 power 5. For example, I have any number of possible combinations, the maximum possible combinations are 2 power n. The maximum possible combinations are 2 power n. So this is the very simple procedure to identify the maximum number of possible combinations. Okay, so here the hexadecimal value is equal, the hexadecimal base is 16. So this is the 16 and you have to represent that value into 2 power, that is 2 power 4. 2 power 4 is equal to 16. 2 power 4 is the maximum possible combinations if you have 4 digits. So this is the condition, here it is satisfied. That is, by using 4 digits you can represent the maximum possible combinations which you will get in the binary number system. Okay. Right. Next, each group of 4 bits are representing with a hexadecimal digit. Here we discussed that I have the binary number. Now I want to convert this binary number into hexadecimal number system. So the binary numbers are zeros and ones. So the input is zeros and ones. Now I will take one example here. I have zeros and ones input. So the same example we discussed in the octal to decimal conversion system. So we will see here. So 101110.01. So this is a binary to octal conversion. So the same example I have taken here for converting binary to hexadecimal system. So here in the octal number system, the maximum possible combinations are 2 power 3, that is 8. So with this 3 I did 3 groups. Now the possible combinations are 16, that is 2 power 4. So I made the binary digits. Now I will group the 4 bits of binary. Now I will group the 4 bits here as one group. This group is representing, what is the value of 0 1 1 0? That is 0 1 1 0. So that is 6. So this is 6. Okay, from the decimal point. So see here, this is the decimal point. This is the decimal point. From this integer part, you have to start. From this, you have to make the group. Oh, for example, integer part is there. Towards left side, you have to make four groups of bits. Otherwise, fractional part, you have to move right side. Right? Here, there is no digits. Left side, you can add so many zeros. It's not a big problem for integer part. For fractional part, you can add right side any number of zeros you want, you can add. So now this is a 4 group, this is a 4 group, this is a 4 group, right? And this is the decimal point. Okay. Right. See here, I am placing 0, 0, 0. 3 zeros I have added here and 2 zeros. For making 4 group, I have added these zeros. Right. These 4 groups are representing, see here I am assuming here zeros, and so the value of this one is 6. Next this value 0, 0, 0, 1. So 0, 0, 0, 1. The value of this one is 1 in decimal representation. Okay. Right. Now 1. So in the hexadecimal or decimal, the 0001 is representing 1 only. So here the value of this one is 1, the value of this one is 6, and the value of this one is 4. That is 0100, 0100. So this is the 4 value. So the value is finally 16.4. For the given number, the output is 16.4 of base 16. So this is the finalized answer. You can convert from this binary to hexadecimal and hexadecimal to binary, right? So the same type of conversion we can use for the hexadecimal to binary, binary to hexadecimal. So this is a conversion technique. We will take one more example now. Now we will take one more example. For example, I have 1 0 1 1 0 1 1 dot 1 0 1 1 0 1 0. So this is the biggest number I have taken. Now my motto, I want to convert this number into hexadecimal. The number seems to be very big, but the answer is very simple. So see here what I said here. So this is the decimal point, right? Is it visible? Right. So this is the decimal point. From the decimal point to, you have to come left side or right side by making 4 groups. You want to convert into hexadecimal. So for that reason you have to make 4 groups. So these are the 4 numbers. Next these are the 4 numbers. And these are the 3 numbers. There is no number here. So for that reason I am adding 0. Next. Toward this side also. This is 4 group. This is 4 group. Here you have to make 4 groups. You have to make 4 groups. Here only 3 digits are there. Place 0. Okay. Now what is the value equivalent this one? What is the value equivalent for this one? Okay. 1011. So what is the value of 1011? How to find the decimal value for this one or hexadecimal value for this one? If you got the decimal value, you can convert into hexadecimal. So see here, I said that use 8421 code. If the digit is 0, cancel this one, and the remaining values you have to add here. 8 plus 2 plus 1. What's the value here? It is 11. So the value is here 11. But in hexadecimal, we don't have 11. What is the 11 equivalent value in hexadecimal? That is B. Okay, so 0 to 0, 1, 1, 2, 2. So this is decimal, this is hexadecimal. Okay, this is 2, this is also 2. And 9 equivalent value 9, 10 equivalent value A, 11 equivalent value B, 12 equivalent value C, 13 equivalent value D. Right? So you have to remember these values. Every time you have to remember these values. These are the very important. The total subject is completely based on these number systems only. So for that reason you have to practice more number of times. Right. Okay. Right. So the value is here. This is representing 11. here the value is 11, and here this value 1011. Again you will get 1011. What is the value of 1011? 8 to 1, that is 11. That is equal to, again this value goes B. Next, this value 0110, this value is 6. Next, this value 1011, this is B. 0101, the value of this one is 5. 1010, the value of this one is A. Friends, 10 equivalent value is A. You have to remember, and you have to convert into hexadecimal, not into decimal. You will get the decimal values, but you have to represent with the hexadecimal representation. So the final value is 6BB dot B5A of base 16. So some of the more functions are there. 6BB dot B5A. So this is the conversion technique. If you want, you can note down. Oh, this is erased completely. Okay, do practice. See once again the procedure. Once again I am saying that. So if you want to convert from binary to hexadecimal, the given value you have to see here first. So if you have integer and fractional part too, you have to make 4 groups from the decimal point. Otherwise, if you have only binary number, for example, if you have only binary number, make 4 groups and give the final value. That is a very simple thing. If you have fractional part too, if you have any fractional part from the decimal point too, you have to make 4 groups right side and left side also, and you will have to convert. You have to convert this value into binary. So this is also works both ways. So binary to octal, binary to hexadecimal, it will works on 2 directions. Okay. So this is the conversion techniques. So and next we have one more conversion technique. We have one more conversion technique that we will see in the next class. Right. Octal to hexadecimal conversion technique. So our class is completely now. We will discuss about with this topic. The topic is right. So in the last class we have seen different types of conversion techniques. We have total 9 conversion techniques. In these 9 conversion techniques we have seen 8 conversion techniques. Now we will start this 9th conversion technique. So that is octal to hexadecimal conversion. So octal number system is 8 and hexadecimal base is 16. That is base 8 to base 16 conversion technique. So in the previous classes we have conversion techniques we have converted from one number system to another number system directly. Okay, but in this conversion technique we are using an intermediate step to convert this number. That is, to convert binary to hexadecimal we have to use an intermediate step. So that intermediate step is nothing but as base 8 to base 16, base 8 to base 2, base 2 to base 16. Okay, from the octal number system to binary number system to hexadecimal number system. So you already know that how to convert octal to binary, binary to octal, and octal to hexadecimal, hexadecimal to binary number system. How to convert these techniques we have discussed in the previous. Now we are merging those two concepts. That is, from octal to hexadecimal I am converting. For example, I have 26.2. So this is in octal number system. Okay, for this the equivalent binary number system. For this, we need the binary equivalent number. What is the value of 6110? See here, the octal numbers you can represent in binary by using 3 digits only. You don't have any right to take 4 digits. Okay. So if you want to represent an octal number in binary, you have to use maximum 3 digits only. Don't consider 4 digits. With using 3 digits you can represent. So the value of 6 is this one and 2 is 0, 1, 0. So this is the equivalent value 2. And next decimal point. So this is a decimal point. Next 2 value is 0, 1, 0. Right? So this is the binary equivalent number. Okay, this is the binary equivalent number. What we did in the previous conversion technique, the same technique we are applied here. So 26.2, 6 equivalent octal binary number, that is 110. Next 2 equivalent value 010. Okay, so this is the equivalent values. Right. Now binary to hexadecimal. How we converted from binary to hexadecimal? For the given binary number, if you have any fractional part and integer part, both parts if you have, from the decimal point to left side of the integer part, right side to the fractional part, we made 4 groups. Okay, we made 4 groups. Here I have the binary number. Now I am erasing this 3 groups concept. Now I have from where I got this number, I don't require anything. Now I want to convert from binary to hexadecimal. How we will convert binary to hexadecimal? You have to make 4 groups. So this is 1 4 group and next 4 group and this is the next 4 group. So here for making 4 group, here we have only 2 digits. So for that reason you have to represent 2 zeros more, and here you have to place 1 0 for making 4 group. Okay. Now value of this one is 1. The value of this one is 6, and here we have decimal point, and the value of this one is 4. So this is the equivalent value in hexadecimal. Okay, so I said that the conversion technique from binary to hexadecimal, hexadecimal to binary, the process is same. Okay, so for the 6 value, you have to represent 0 1 1 0. Right? See, this is very important concept. For example, 6 is there. If you want to represent in binary, you have to represent 110 only, 110 only. If you want to represent in hexadecimal, you have to represent 0110. So this is in octal, this is in hexadecimal. Right? If you want to represent the 6 in octal number system, you have by using octal number system, you want to represent in binary, you have to write 110. The same number you want to represent in hexadecimal, you have to represent with 4 digits. That is very, very important. You have to remember this point. Okay, if you want to represent this 6, which one is there in the hexadecimal? This is the hexadecimal number. This is the octal number. This is base 8. This is base 16. Okay, 6 of base 8 you have to represent with 3 digits of binary digits. That is 110. The 6 which will be there in hexadecimal number system, that you have to represent with 4 digits. This is very, very important. Right. Okay, we will see once again this process. First, I have to take 26 of 8. First, I have to take 26.2 of base 8. So that is octal equivalent number I have taken for this problem. Now I want to convert this into binary number system. So 6 equivalent value, and this is 2 equivalent value. 6 equivalent value is 110 and 2 equivalent value is 010 and 2 equivalent value is 010. What I did here, the octal equivalent binary numbers I have represented here. That is very simple concept. Next what I did here, I made 4 groups. Now I made 4 groups. This 4 group, and I have to take one more 4 group here, and I have to take one more 4 group here. Total of 4 groups I have to take. So the 4 group of this one is 6. The 4 group. So remaining you have to put 0 0 0. So the value of here it is 1. Next 0 1. For making 4 group you have to add one more 0. That is 0 1 0 0. That is the 4. So 16.4. This is the hexadecimal equivalent number. So finally, Finally, 26. Finally, 26 of 26.2 of base 8 is equal to, in hexadecimal the value of this one is 10110.01 of base 2, and that is equal to 16.4 of base 16. So this is the final solution. 26.2 of base 8 is equal to 10110.01 of base 2 is equal to 16.4 of base 16. So this is the octal to decimal conversion technique. Okay, this is the octal decimal conversion technique, right? And you have to do a lot of problems on this concept. We have to work on more number of problems. Then only we will, if the practice is very heavy, then only we can learn the subject easily. So for that reason, make the practice. For this concept, you have to follow the textbook is Digital Design by Maurice Mano. So at the end of this unit, at the end of the first unit, you will have 30 to 40 problems. All the 30 to 40 problems are very easy. Almost all the conversions are based on these 9 conversion techniques. These 9 conversion techniques, internally it has just 2 to 3 small basic ideas. With that basic ideas only we did all these things. Okay, thank you. Okay, so in this class now we will see the power of 2, right? That is, we will see the sizes, and generally in the digital side we are calling as memory. Our pen drive 64 GB we are saying. Okay, our mobile has internal memory of 2 GB, internal memory of 64 GB, and RAM of 4 GB, 6 GB, 8 GB. For example, all the mobiles presently we are running with 4 GB memory, 4 GB RAM. Okay, and some of the gaming mobiles are presently available with 6 GB, 8 GB RAM also. Okay, what is that GB? Okay, what is meant by that GB? That we will see now. Okay, and not only GB, KB, MB, we have different types of notations. What is their notations, that we will see. Okay, here first see, in the digital side, if you have 0 or 1, okay, either 0 or 1, it is called bit. 1 is called bit and 0 is also called bit. Okay, right? For example, I have 10101. Okay, in this group, how many bits are available? Total 5 bits are available. Total 5 bits are available here. Okay, right? That we will see. Right here, I have 0 bits. That is 2 power 0. I have only 1 bit. So that is 2 power 0 is equal to 1. For example, n is equal to 1, 2 power 1 is equal to 2. Just first listen this mathematical calculations. That is 2 power 1. What is the value? Here it is 2. 2 power 2, that is 4. Here the 3, 2 power 3, that is, I am taking 2 power n here. Here I am taking 2 power n. Now, if n is equal to 0, 2 power 0 is equal to 1. If n is equal to 1, if n is equal to 1, 2 power 1 is equal to 2. If n is equal to 2, 2 power 2 is equal to 4. If n is equal to 3, 2 power 3 is equal to 8. If n is equal to 4, 2 power 4 is equal to 16. If n is equal to 5, 2 power 5 is equal to 13. In the same way, n is equal to 7, 2 power 7 is equal to 128. If n is equal to 8, 2 power 8 is equal to 256. So this is very important. See here, we have all the n values, but this 10 is very important. 2 power 10 is equal to 1024. Okay, so generally for 1 kg, how many grams we have? For 1 kg, how many grams we have? Nearly 1000 grams. 1 kg is equal to 1000 grams. Here, this 10 is very important. 2 power 10 is equal to 1024. Okay, so if you are measuring liquid items, for example, milk, water, if you taken, 1000 grams is equal to 1 kg. 1000 ml is equal to 1 liter. 1024 we are calling as kilo. Right? Next, if the value n value is equal to 20, that is 2 power 20, that is nearly 1 mega, that is we are calling as 1 mega. 1024 kilo is equal to we are calling as 1 mega. Next 2 power 30, that is n is equal to 30, 2 power 30, that is 1024 mega is equal to 1 giga. Next 1024 giga is equal to 1 tera. So generally our hard disk is 1 terabyte, 2 terabyte. Our mobiles are 64 GB. So see here, we will see that with bits combinations. See here, 8 bits are called See here, 8 bits are called 1 byte. 8 bits are called 1 byte. Here I am represented with 1 byte. Here I have mentioned the abbreviations. Here I have given the full forms. These are very important. 8 bits are nothing but as 1 byte. That is generally we are calling as 1 byte. That is the same full name. Next, 1024. That is 2 power 10. 2 power 10 bytes, 2 power 10 bytes is equal to 1 KB, 1024 bytes. See here, 1024 bytes is equal to 2 power 10 bytes. That is we have seen in the previous slide. So see this previous slide. 10, if n is equal to 10, 2 power 10 is equal to 1024. The 1024 I am representing with 2 power 10 bytes. That is 1 KB, that is 1 kilobyte. We are calling this one as 1 kilobyte. Next, this is 2 power 20 bytes or 2 power 10 KB. 2 power 10 KB. 2 power 10 means 1024 KB. 1024 KB is equal to 1 megabyte. Right? 1024 KB is equal to 1 megabyte. I have written here the expansion. I have represented here the abbreviation. 1 MB is equal to 1 megabyte. Next, this is 2 power 30 bytes. Or you can write 1024 MB. 1024 MB. 1024 MB is equal to 1 GB. So simply remember like this. So here 2 power 20 bytes, 2 power 30 bytes, here 2 power 40 bytes. You can represent with this notation also. Okay. So finally this is 1 TB. So 2 power 40 bytes are 1024 GB is equal to 1 terabyte. 1024 terabytes is equal to 1 petabyte. 1024 petabytes is equal to 1 exabyte. 1024 exabytes is equal to 1 zettabyte. So 1024 zettabytes is equal to 1 yottabyte. So these are the total bits and their representations. So this is very important notations. Presently we are using bytes, kilobytes. Presently we are using bytes, kilobytes, megabytes, gigabytes, terabytes. Presently we are using terabytes only, commercial purpose. For the scientific purpose, for the database purposes, we are using petabytes also. We are using petabytes hard disks also. So presently these are in the under construction process only, where we are going to see the very deepest micro or sub-micro or deep sub-micron or technology in the coming days. At that time we have the memory with availability of this one. Okay, right. Next we will see the conversion techniques by using an online software. So see here, this is a software called rapidtables.com. In this website, here which number system to which number system, if you want to convert from any number system to any number system, for example, see here we have binary number system. Now the software is going to convert into decimal number system, binary to decimal. Otherwise, if you want to convert with any number system to any number system, so here they are given binary, decimal, hexadecimal, and they are going to convert into binary, decimal, hexadecimal. So they are given four different types of numbers, three different types of number system. We have a lot of websites. In these websites, we have the 4 number system conversions. Otherwise, total 20 number conversion system or 100 number conversion system. Whatever the number system you want to choose, you can choose. Not only 2, 10, 8, 16. So other than this also you can select, and you can do the same operation by using your calculator also. Okay, for example, see here, binary to decimal. So you have to give the binary value and you have to ask them convert. Otherwise, now we will see. I will add some more zeros also here. So I have given some binary number. I have used the convert option. Now the value is 1756. Right? We will see one more also. So I have given some more digits. Now I am going to converting this value. So what is the value of this one? 1,12,441. You can convert in this way. Otherwise, take decimal number and you want to see in binary number. Now reset everything. Right? Now give the decimal number. For example, 963 to 9632. I have given this number. Convert this number into binary. So the binary number we got here. But the same operation we can do by using our calculators also. That I will share with the next video. So in this is the one of the possibility for verification your answer is correct or wrong. Okay, you have to practice a lot of problems. For that problems you have to convert this one, and finally whatever the digits you got that correct or not, you have to check with these online conversion softwares. Otherwise you can use your calculator also. Thank you.